probability experiment. So again, sometimes we use fancy terms for things. Numerical outcome. That just means a random variable is always a number, right? You guys learned before about qualitative variables, right? Those are not numbers. Random variable is quantitative, so it is a number. But it comes from a probability experiment. Anybody remember what a probability experiment even is? One of those terms you see and go, oh, I kind of remember that. So just remember, a probability experiment, you remember, is an experiment. If you can't read this, let me know. Like I said, this is weird for me here. A probability experiment, remember, is one which we don't know any given outcome but do know over a large number of repetitions. So this will be in your notes. You don't have to write all this down again. From last week, I just want to talk about this for a sec. Just to remind you, remember, you talked about probability experiments last week. One was rolling a die, right? A cube die that has 6 sides. If you roll a die, you don't know what it's going to come up, but you know as you keep rolling it more and more times, you know the probability of getting a 1 or a 2 or a 3. So that's a probability experiment. So this first section will always talk about outcomes of probability experiments. So random variable comes from a probability experiment. And die is a very simple one. So again, if you have a fair die, assuming they all come up the same, everyone has a probability of 1/6. Again, that doesn't mean if you roll it 6 times, you'll get 1 of each, right? But if you keep rolling it over and over, you will. So they use the variable x for our random variables. So whenever you see an x in this section, that is my random variable. So we'll just see this off and on all day. Now the other thing is, what we're going to talk about in here is discrete random variables. And later on we'll be talking about continuous, which remember, you have 2 kinds of variables, discrete and continuous. So they give you some examples in your notes on continuous and discrete, right? So a discrete variable is rolling a die. You got that one. Number of siblings. Any other random variable or any other variables that are discrete that you can think of that you might have talked about before?
The number of siblings you have.
Number of siblings, right? Siblings. How about the population, right? Of a school, a country, the world. So all those are discrete. Now continuous, they list a couple here. Height. Again, one thing that throws students sometimes is we always round, right? I don't say I'm 5'9", 1, 2, 4, 7, something, right? I'm 5'9". But height we could carry out to as many decimals we wanted. Same thing with range. What's a couple other continuous random variables?
Time.
Say it again?
Time.
Time, thank you. Time. Right, again, we round. We don't carry it out, but time's another one. Length. So any of those are continuous random variables. But again, what we're going to talk about in here at the first part are going to be discrete random variables. So, now, we talked about this previously, so this is just kind of going back over it a little bit in terms of random variables. So you remember before, they called it a probability model? So in this section, when you're talking about a random variable, they just changed the words a little bit. It's called a probability distribution. So, again, a probability distribution just tells you what the probability is for each of your random variables. So similar to what we did before, there's two properties that you have to remember anytime you're talking about a probability for a random variable. The first one is your probability for any of the outcomes has to be between 0 and 1. Just remember that. And second, make sure it's the sum of the probabilities equals 1. So this just says if I take the sum of all the different possible outcomes, it has to equal 1 when I'm done. So this is very similar to what you did in the last chapter when you talked about probability models. Different terminology, same idea. Stop me if you have any questions. All right, so on the next one, probability distribution. Just like our probability models, this tells us what the probability of each of our potential outcomes is. So on your sheet, it says X is the number that comes up when a fair die is rolled. Now, sometimes they do this horizontally, sometimes vertically. On your sheet, it's vertical, right? I'm gonna do it horizontally just to show you. It doesn't matter. Sometimes they switch these around. But X is your potential outcomes. So if I roll a die, you get up to 6, right? And again, if it's a fair die, the probability of each of those outcomes is just 1/6. So in some cases, you'll be looking at probability distributions or potential ones and seeing if they are. Other ones, you get to create your own, depending on the problem. So again, what are the two properties? A probability of an event has to be between what,
0 and 1.
0 and 1, and the sum has to be 1.
1.
So if you look in your book, on page 209, I'll look at my book. So take a moment before you give the answer. And if you don't happen to have a book, you can answer those if you'll share if you happen to. What I want you to do, just take a moment. And look at those 5 distributions and see if those are a probability distribution. So take a moment and determine that, and then we'll compare answers. And while you're doing that, I'm gonna pass around an attendance sheet, if you would. Put your name on there, and pass around, please. Okay, so on 27, is 27 a discrete probability distribution? Yes. How about 28?
Yeah.
29? No. All the probabilities between 0 and 1, but the sum is not 1. 30? No. Again, you can't have a negative. So if they give you one and you have see a negative probability, you don't have to add them up or anything, you know it's so. 31? No, they're all between 0 and 1, but if I sum those, what do you get, 1.5? So that one doesn't work either. And last but not least, yes. The reason is your random variables, your x's can be negative, but just the probability can't be. So the fact that you have negative outcomes is okay, depending on the problem. All right. So again, that's nothing really new. We're just talking about a little bit different terminology for you. So now we get to come up with a probability distribution. So on the next page, it says we have a town that has a population of 1,000 households. We have 142 of them that have no car, 378 have one, 423 have two, and 57 have three. If you choose a household at random, X is going to represent the number of cars in that house. So to set up a probability distribution, you still list the possible outcomes, right? So the possible outcomes is you have no car, 1, 2, or 3. That's all my outcomes. And then you come up with a probability for each of those outcomes. So you take how many have each of those number of cars, divide by the total. So again, we had 142 people out of 1,000. And they made the math nice and easy for us, because they divide by 1,000. And then the second one, let's see, 378 have one car. $423 have two cars. And last but not least, we had 57. That had one car. Or three cars, rather. So this is my probability distribution. Now, they don't ask you to, sometimes it's good if you actually sum these up, make sure you don't make a mistake, right? If I add all these together, what should be total be? 1. So if somebody would check my math here, it looks like it'll come up perfect, because that's 1. So I'm gonna guess it's right. You'll have to let me know, just in case. That come up right? Now, it's possible you could be off, right, just because of rounding, so that is possible. And that's why it's always good to carry these out to more decimals rather than fewer. All right. Issue. So that's a probability distribution, and now we're going to create a histogram. Right? I'm guessing all of you are working on histograms for your projects this semester, right? Are they relative frequency or frequency distribution, or that's histograms? There you go. Frequency, okay. So when you talk about a probability distribution, you're going to be talking about relative frequency, because everything's gonna be relative. Okay? But the histogram here is going to be very similar to what you would have done previously for a relative history, a relative frequency histogram. Now again, this is for discrete. And remember, a histogram does not have a space between your bars. And since my lowest bar is a 0, I can start in the corner. And so this relative frequency, so remember what you do is you look and say, okay, how high do I need to go? You don't have to go up to 1, because none of these bars are gonna go up to 1. And actually, she gives you space before I get too far ahead of myself on the next page to create this. So you just go in order from your distribution. 0.142 is right in here somewhere. So you get a 0. 0.378, right in here somewhere. 0.423, up here somewhere. And last is 0.057, which is down here somewhere. And again, one thing is when you look at a book or look at what different instructors do, when it's discrete, I like to put the value in the middle. It's not wrong to put it at the right, or at the class end, but I like to put it in the middle. Now, the other thing I like to do, I don't remember if she does it, so if she does it, you don't have to. Just because, when you look at a graph, if you don't have the distribution, you don't know exactly what the number is. So what I like to do is I like to put the number, either the frequency or relative frequency on the top of the bar. That way, just by glancing, you can tell exactly how tall the bar is. Again, if she doesn't require it, that's fine. I don't remember if she did or not. So you can create a probability distribution histogram, which is just like a relative frequency one. So far, so good. Any questions? So a lot of this is stuff you've already seen, just a little bit different format. Now the next thing you do with all this is find probabilities. So if you look on your next page, if I just randomly, if I put all 1,000 names or households in a jar and I drew one at random, you want to know the probabilities. The first example she lists for A says find the probability of 0. And what that really means is what's the probability if I randomly choose somebody's name out of a hat that name or that household will have 0 cards. And so you just look off your distribution or off your histogram. Right, so it's 14.2% or 0.142 is the probability that you would have 0 cards. B says find the probability of at least 1. Take a second, and based on the data up here, figure out what the probability of having at least, if you picked a random family out, what's the probability you have at least 1?
86.8.
I have no idea. We'll have to calculate it.
858.
I'm just,
So if you're gonna have
because we
at
had-
least 1, you're gonna have that, right? Now, how did you calculate it when you did it?
I just took the A and we had 14% chance of,
Right. And what is that called when you do it backwards? I call it backwards. So what you really did is you said, I'm gonna take the 1 minus the probability that they don't have any cars, right? which is 1 minus 0.142, which is 0.858. This is called the complement. Remember complements? Now, how else could you have done it?
Could have added them.
You could add the three together. And there's nothing wrong with that, but if you have 20 things you have to add or subtract one, it's a lot easier to remember this. So always remember the potential of using the complement. So again, once you have the distribution in front of you, it's not too bad to come up with these different probabilities. Questions on that? I'm assuming silence means consent and you know what's going on. Again, this is kind of just a new version of what you've done before, different terminology. But you've seen some of these before, so that's good. Now, the next thing, when we get into statistics that we always want to find for some reason, we want to find the mean and we want to find the standard deviation. We always look for those. So if you look on your next page, if I want to find the mean of a random variable, I'm going to erase my histogram here, and I'm going to leave that up there. If I want to find the mean, remember notation for mean is mu, and the little x is only there because we're talking about a random variable x. So the mean of my random variable, you take the sum of whatever the outcome is times the probability of that outcome. And I didn't see it on this chart. Okay, I think it comes up in a few minutes. You'll have a note on one of your pages that says, be sure to know how to do this by hand. So you have to know how to calculate the mean. So if it gets too loud back there, let me know. I'm just trying to get some air in here. All right, so to calculate the mean, remember the sigma just means sum, I'm adding together. So what you're going to do is you're going to take your x value, your random variable, times your probability. And I realize because it's a zero, you can ignore it. I'm not going to ignore it because I want you to remember that it's there. Then you take the next random variable, 1, times 0.378, plus 2, times 423, plus 3, times 157. So this becomes a calculator exercise once you know how to list them out. So once you ran the numbers here, what did you come up with for the mean for this thing? .395. Anybody want to second that? All opposed? This is like a political election. You have one person voting and nobody else votes, so you get to select who wins. 1.395, and that is correct. So this is the mean, which another name for arithmetic mean is average. So what this tells us in this case is if I had, again, all 1,000 households in a jar, and I drew out a name or a household, let's say the first one had 1, and I put it back. The second one had 3, I put it back. If I kept doing this many, many times, and added up how many cars those families had, the average, or the mean, would be about 1.4. So the average number of cars for those households is 1.4. And that's where the little note is. I know I saw it this morning somewhere. For the homework and the test, make sure you know how to calculate, how to use this formula, and make sure to show your work. Okay. I bet the next thing is standard deviation. It is. Okay. Now I know your notes are a little bit different than mine. I think all this is on your notes. It says you're gonna use the calculator to calculate this, is that right? So for some of you who like formulas, I'm gonna put the formula on the board, but you will not have to do this by hand. So you remember, when you're talking about the standard, the variance of a population, that's sigma. The little x again just says our random variable is x. So what we're gonna do is we're gonna take the sum of our x values minus the mean squared times the probability. That will give us our variance. And remember the standard deviation is just sigma, and that just always equals the square root. Always remember that. Never forget that. The square root of the variance is always your standard deviation. Like I said, you don't have to know that formula. It's in your book, but it's kind of nice to know. And again, this really goes back to the formula you did before when you had variables and you found the mean and standard deviation. It's very similar to that formula. I think we're done with the card, almost. I shouldn't have raised my card, but that's all right. You can all help. Because now we're gonna use our calculator to come up with these things. So, now that I erased my picture a little bit early, let's see, this was 0.142, 378. Is that close? All right, so we're gonna use the calculator to calculate standard deviation. So to do that, you're going to use your one-var stats again, like you've done before. And you remember the way you do this is you create a list. So in L1, you're going to put your random variables, whatever those are. Does anybody need a calculator? I saw you looking at your other. Poor girl back there used to have me and she didn't think she'd ever have to see me again.
I think I deleted my L1.
Ah, that's it. So use L2 and 3, and I'll show you how to, remind me on break, and I'll show you how to put it back. But that's not uncommon. Rather than, it's really easy on your list. If you go up and you want to clear it, if you hit clear, it goes away. If you hit delete, it wipes out the whole column, including the title. And that's okay, that's easy to fix. So L2, or in your case L3, would be 0.142 .2378, .433. Everybody else have a calculator?
So this one, the X, and this two is gonna be the probability
Correct.
minus.
Exactly. And if you have any questions on putting this in, because this is important.
Is that times P or minus P?
I'm sorry, that's supposed to be a times.
Okay.
If you have any questions at all on putting this in, let me know. I want to make sure, obviously for your test and to do your project, you need to know how to do your one variable stats. So once you've got those in your list, go back out and go into, anytime I've done this, go into stat, and then your one variable stats. Go over to calc, and then one variable stats. And then you're going to have in the first, now again, if you have an older calculator, what you will do is put L1 and L2, or in your case, maybe L2 or 3. If you have the newer ones, it actually lists them out for you, right? It stacks them. The older calculators like this one don't do that. And the comma, remember, is above the 7. So if you need to put a comma in on yours, it's above the 7. And then that should calculate your mean and your standard deviation.
So for list one, the line is seven.
Just do the second.
And then you do
Okay, so pretty much what you do.
that is L.
Yeah.
That's all I have on that. Is this supposed to be L1 and L2? Yeah. How are you supposed to see L2? So I did it in my list. Okay. Okay, now it's.
And you can tell if you're right, because the mean that shows up on the
How do
calculator
you get the frequency list?
will be 1.395.
I can't do the comma.
Wait,
Oh, sorry, you can,
The
because you have a nice new calculator. So you need a second.
Do you ever have like
The old phones where you had to go over to.
Yeah, we did.
Right. Now, the second calculator, the older one gets better.
You are?
Yeah, it doesn't even feel comfortable.
Yeah, mine's not letting me put a comment in.
How do you put a comma?
Yeah, like,
So the comma is right above the, oh, it's like, you don't need a comma. Sorry, you have a newer one that actually stacks them for you. So go back, so you want to change that one to L1.
Or just list two.
Yeah, okay, you're good, okay.
That's like project like that, because that's what list
Yep.
one.
Yep,
mine
you're
won't.
good.
So I don't need nothing.
alright, this thing is,
Yeah, so the newer calculators are the ones that stack them.
alright,
The newer calculators do this. And for most of you, it'll be L1 and L2. But if the older calculators don't do that, they just show you this, and then you have to put that in. Everybody come up with 1.395 for your mean. That's how you know you did it right. And then your standard deviation,
1 point. Okay.
to 4 decimals, What did you come up with the standard deviation? Somebody be brief, I heard it. That's it.
Isn't it? My numbers don't match.
The mean is the top number, so ignore the second, the mean is the top. Okay, so what then?
I have to. Nothing we can really do.
Oh, okay. Okay, cool.
Yeah. I'm looking at his house.
No, not
Yeah,
that.
Yeah. It'd be really awkward if I didn't.
All right.
Say what list.
Yeah, she lives there.
Maybe fly on top of
So everybody come up with these numbers. So what does the mean tell you? Remember, the mean is the measure of center, where your mean average center is. What does the standard deviation even tell you? It's a measure of spread or dispersion, how far apart. We're gonna talk more about that in chapter 6. Something to look forward to. Okay. All right. Okay. So we're just going to expand a little bit on the idea of a mean, or the mean here. In some instances, when you're investing money, maybe you're playing the roulette wheel, whatever it is, you want to figure out in the long run what your outcome is going to be. So if you're looking at the outcome over a number of events, instead of calling it the mean, they sometimes call it the expected value. And the notation they use is a capital E. But mathematically, that's the same thing as coming up with the mean. No difference. Now the difference is, the only difference is really, is if your expected outcome is negative, it's a loss. If it's positive, it's a gain. So look at the next page and the example on the next page. It says a mineral economist estimated that a particular mining venture had a probability of 0.4 of losing $30 million, probability of 0.5 of a $20 million profit, and a probability of 0.1 of a $40 million profit. Does this venture represent an expected gain or an expected loss? So whenever you see the term expected, like on your test, which I'm willing to bet you'll have one question on that. I don't know, but I'm betting you anyway. So, think of probability distributions and means. So it's gonna be the exact same thing you just did. You have your potential outcomes and the probability of those outcomes. So if you look at your outcomes, I can have a $30 million loss. Remember to make that a negative, right? I can have a $20 million profit or a $40 million profit. Quite a big swing. The probability of a loss of 30 million is 40%, which is pretty high. 0.05 and so if they ask you to calculate the expected value, that's the same thing you just did a moment ago with the mean. So the expected value, I think that's the next page. Yes, the next page. She left you space to calculate. So, if I wanna calculate this, remember you take the sum of your x values times your p of x. So it's negative 30 times 0.4 plus 20 times 0.5 plus 40 times 0.1. And that's what, negative 1.2 plus 1 plus 0.4. Nope, plus 4, sorry. Am I doing my decimals right here? 120, that'd be, no, that would be 12. That would be 10. I messed up my decimals. So 30 times 0.4 is 12, 20 times 0.5 and 40. So after all that work, I get 14 and negative 12, which is 2. Now, I'm really picky on units. This is 2 what? $1 million, exactly. That would be my expected value. Now, the thing is, what this really says, because if you go into a venture, you either make money or lose money, right? But if I keep going into the same venture with the same distribution here, time after time after time, in the long run, you'll come up $2 million ahead. And I'm very conservative, I probably wouldn't do this. Because the first time you did it, let's pretend I lost $30 million. Darn. So the next time I did it, let's say I lost again. I'm now 16 million in the hole, I haven't made a penny yet. Let's say I do it 3 times in a row. Then I turn around and start making money. But in the long run, if I kept doing this over and over, I would end up with $2 million. That's how the casinos get you, right? You go in, you win the first time, you think, all right, this is great, then you lose it all, then you want to gain it back. So anytime you see expected value on the problem, think of calculating the mean. The math is exactly the same. Questions on that? Well, that was too easy. We've already covered the first section. Wow. So does she usually give you 1 breaking bell or 2? One. All right, well, today I'll give you 2. We'll make it a short one. So everybody get a little break. Come back.